So here we can see our first 3D problem, the 3D cable structure with a spring included. The spring actually goes from node A to node B. And our problem here states that we are supposed to determine the stretch in spring AB. And you already remember from the previous class that we worry about this at the very end. So first we have to find all the forces in the cables. And let's look at this cable structure here. So first of all, we have 90 pounds acting downwards. That's the weight, the traffic light or whatever you want to put there. Then we have a cable that goes upwards. And now take a look at this 3, 4, 5 triangle. It states clearly that the 3 is parallel to the Z direction and the 4 is parallel to the X direction. So therefore this hook here actually resides within the XZ plane and it has 0 Y component. So this cable has no Y component. Similarly, this cable here, it can be a little bit deceiving, but notice that there's only the 30 degree given here. So that means that D actually resides within the X negative Y plane with a 30 degree separation from the negative Y axis. And then clearly, I think, is stated that AB is along the y-axis. So now we can solve this. And maybe the first thing I'm going to do is actually superimpose a little free body diagram. And since I can zoom in here and make sure that we understand that it's really acting at this node, I'm going to draw the free body diagram for node A here. And what I will find is that I have forces in all 3 directions, but differently distributed over the cables. So for example, I have a force that is acting in this direction, and that here would be, let me zoom out, that would be AC, right? So ACX in this case. I also have a force that's going upwards, and that is AC Z in that case. And as I mentioned before, that cable has no Y direction, so I'm already done with that one. Let's move on to the next cable. Let's say we're going to do AD next. So AD has no Z component, but it definitely has a Y component that goes in this direction. So I'm going to call this ADY, which is acting in the negative direction. And I have also a X direction force. So let's draw that one. Let's say that's acting right here. Of course, in reality, that's right at the node, but it shows it better at this location. So ADX. However, in reality, it's actually acting right here, right? So this is another representation of ADX. And last but not least, I have the force in the spring, and that force is acting in this direction, and I call that AB. And that is technically ABY, so it's equal to AB in this case. And for completeness reasons, I probably should also add the forces, the entire forces, the summation of them. So let me add the blue one first. So I have a force here, which that is pulling in this direction. Call that AD. And then I have AC along this line here. So I'll call this here AC. Before I move on, let me just clarify that we effectively superimposed the free body diagram on the sketch, which is not the right way to do it, but just to get the point better across here, since we're not in the classroom together. Let me just explain one last time my cut philosophy here. So I cut the system, let's say here, maybe here, maybe here, maybe here, and it doesn't really matter how large it is, because so I have this entire cut system here. And I could, of course, also cut, let's say, here or here or here. But I want to make sure that we all understand that we're pulling on this node here at the origin of the coordinate system. So this is actually a coordinate system for an introductory problem, so that the coordinate system coincides with that free body diagram, if you will. This may be different on later problems, but I hope you understand that we're just looking at that one node. And that is one reason why, for example, we can ignore the spring, for example, right now, and we can move our way through the problem now. So let's go ahead and do something that we would never do in practical applications, but from an educational standpoint, it's the right thing to do. And that is writing down blindly the equations and, of course, before we do that, the conditions. So this is something I would do on an exam if I wasn't properly prepared. I would just blindly state that the sum of the forces in the x direction is equal to 0, and the sum of the forces in the y direction is equal to 0, and the sum of the forces in the z direction is equal to 0. And of course, I need to state my directions. X is going in this direction, y is going in that direction, z is going in that direction. And now I can just write down my equations. Of course, all of them start with 0 is equal to something. So let's do that. And then I want to start with my smallest one, which is AB. So in the x direction, there's nothing in the AB direction. In fact, AB only has a y component. And then next is AC. And AC happens to be in the negative direction, so minus ACX. And then last but not least, ADX. And that is positive, right? So plus ADX. And of course, there's nothing actually in the negative direction. So I don't have to worry about that. This next row is the y direction. So here we have plus ABY, so plus ABY. And then we have nothing in the x direction, but we have a negative ADY, so minus ADY, and nothing in the z direction. Maybe we'll show this here. Last but not least, I have the z direction where AB has no z component. You start to see why this is our first introductory problem, right? Because it's becoming very simple now. In the in the AC cable, of course, I do have a z component. So this is plus ACZ, and then the next cable has no component, so I cross that out. But I have minus 90 pounds here. So that now is my equation. And once again, if you're experienced and prepared, you probably would have not needed to write this down. I will show this to you in a second. But for your educational experience, I will now show you how to convert these equations with these many unknowns, 1, 2, 3, 4, 5 unknowns, to 3 equations with 3 unknowns. So for example, I can express ACX in terms of AC. And how do I do that? Let's get started. So AC is really nothing, ACX is nothing else than AC divided by 5. And in the x direction, I have a 4, so times 4. Now, for my AD, which is my blue color, I have ADX, and that is the sine direction of 30, if I'm not mistaken. So plus AD sine 30. And I'm done with that row. Now, for my next row, for the y direction, y is just equal to AB. I don't need to worry about this. I don't need to worry about the red component, but the blue component minus AD, which now is the cosine of 30. And then last but not least, I have the z direction, which only needs to convert ACZ, which is 3/5. And then minus 90. So let's be clear and just highlight what I really would solve for here. So let me pull out my ruler and my highlighter and state that this is the equation that we would solve. This is the equation that we would solve. And this is the equation that we would solve. And to do that 100% correct, I probably should state to you that we have a 0 here at the beginning. So 0 is equal to, 0 is equal to, and 0 is equal to. And what you see now is that you have three equations with three unknowns, right? So we have AB, AC, and AD. And so I can solve this system of equations now. But now it's definitely not my goal to show you how to solve three equations with three unknowns. You have the tools to do that already if you reach this class. The point here is to teach you mechanics. So let's actually go through the problem like I would probably go through it in the real world. And so for that, I'm going to use my logic now. And you will see that by doing that, I can just solve it. So what is my logic? If I look at this system here, there's 90 pounds pulling down. That means that I have to pull 90 pounds up. And the only cable in the system that can actually pull up the 90 pounds is definitely not AB and is not AD because they have no vertical components. So I immediately know that this component must be 90. So let's actually do this even with writing down real numbers here. Let's just say that ACZ is 90. So I know that that is 90. Now I can calculate my other components. I can say that ACX is 90 divided by 3, which is 30, multiplied by 4, which is 120. And so now I know all components in AC. Of course, I could also calculate the magnitude, which would be 90 divided by 3 multiplied by 5, which then becomes 150, but we don't even worry about this, but just for completeness reasons. What I'm really worried about, or what I really want to continue with, is the 120. Because the 120 is pulling in the negative x direction now. And the only thing that can balance that is definitely not AB, right? Because AB only has y components and we're looking for x components. This has no x component, this has no x component. So the only thing left is AD. So I have to pull out of the plane because this is pulling into the plane. So I already know that this component ADX is equal to 120 pounds. And now you see where I'm going, right? Because now I can just take the 120 and turn it into AD. So for example, AD here, right? This force, AD times the sine of 30 gives me 120. So let me write that down. Just so AD times sine 30 would be equal to 120. And so therefore I know that AD is equal to 120 divided by sine 30. And that comes out to be 240 pounds. Maybe I should add that here, pounds. And now, of course, I can calculate ADY to be 240 multiplied by cosine of 30. And if I run the numbers for that, I find that that is 207.8. 207.8 pounds. And now I can continue with my logic, right? I know that this node here is pulled to the left with 207, and the only thing that can pull it to the right is actually the spring. And so I know that the spring now has to carry also 207.8 pounds. And now I'm almost done. Don't get me wrong. We still have to calculate the stretch in the spring. That was the actual calculation. But what I just showed you in physical terms, or like working my way through it, because it's such a nice, easy problem that only has like one vertical and then two horizontal and two in the y direction horizontal forces, that I actually don't even needed this. So this is a very favorite example of mine to get this point across, because every mathematician can solve this, but what engineers need to be able to do is this. And so I hope you get that point, and I hope you understand this. Of course, later on you will not get away with working your way through this, because problems are not always that simple, but in the beginning, this is the way to learn this kind of stuff. And I encourage you to really think about that and understand this. And also maybe validate it, like run the 3 equation with 3 unknowns here and find hopefully the same answers that I just did. But now to calculate the stretch in the spring, let's do that. So the stretch in the spring, so stretch AB is equal to, I always remember my formula that the force in the spring is equal to K times S. And so S is F over K, right? So what is the force that is acting in that spring? It is 207.8 pounds divided by 500 pounds per foot. And so our answer to that is 0.4157 or 0.416 feet. And that is the result, so we double underline it. Be careful, sometimes these problems ask you to find the stretch in terms of inch, and then of course you have to do one more conversion step here, and you have to master the imperial system and multiply this number by 12 to end up with inch. But this concludes this problem now. We solved it, and I believe the engineering approach in this case was much easier and faster than the equilibrium approach or the setting up the 3 equation with 3 unknowns. So now we're ready for more complicated problems, so let's move on. So now our problems can become a little bit more interesting, like this cable structure here, a true 3D cable structure that appears complicated on the first glance, but we will see a few things that can help us in a second. Let's first look at the problem description. So there's a box that has a volume of 3.5 cubic yard and is completely filled with water. Based on that assumption, calculate all the cable forces. And then later on, there's a bonus point for assuming that the box is filled with concrete. We'll talk about that at the very end, instead of water, of course. So let's only focus on the actual initial problem. So we have this box here, which is suspended on a cable that is completely vertical and only directed along the z-axis. But we also have cable AC, AB, and AD. And let's talk about AD first, because that is probably the simplest one, because it has only a force in the x direction. So that one does not contribute in the uplift of the box. But AB and AC do, and that seemingly makes it complicated, but I want you to understand the symmetry of the system. So take a look at these dashed lines here. So for example, node C is actually 8 feet in the negative x direction, 4 feet in the positive y direction, and 6 feet in the z direction. So that is pulling, if you will, towards us. And away from us with very similar components is AB. And what that means is that the system has symmetry about this dashed line, if you will, or I should say about the x-axis. So let's write that down actually, because it is important. So symmetry about the x-axis. And that means that I have half of the weight on the one side of the x-axis and the other half of the weight on the other side. So I can actually simplify my work. So I can actually think of it as half a system. And let me draw that into this here. So let me pretend that I have a force in this direction, in this direction, and in this direction. And my arrows heads go in this direction. So let's call this here, for example, ACX, ACZ, and ACY. And of course, I can do that for the other cable as well. Let's do that just for visualization purposes. So I have this component this component. And the last component, which my ruler does not play along, but it's going in this direction, and this direction. So I can call this ABX, ABZ, and ABY. And you can already tell from this picture now that these two forces together, ACX and ABX, have to be balanced by AD. ACZ plus ABZ have to balance the actual weight. And then ACY balances ABY. So that's how you generate the balance here. And that's why you can actually state now that due to symmetry, AB is equal to AC. And you can also say, for example, ABX is equal to ACX, or ABY is equal to ACY, and so on. Actually, let's complete it because it's so simple to write it down. ACZ. So now I can say that 1/2 of this weight has to be balanced by one of the forces, right? So let's say ACZ has to hold this. So I already know that whatever the weight is of this box, I have the weight in the uplift here. So the first thing, of course, to do then is calculate how much force we have due to this completely filled box with water. So let's analyze that first. So weight of box with 3.5 cubic yard of water. And the first thing we need to know, and of course you know this already, you looked this up a long time ago, is that water in the imperial system has a weight of 62.4 pounds per cubic foot. And that is usually the unit that engineers use in practical life, pound per cubic foot, and not per cubic yard, because we can use this to convert to cubic yard. But be careful, students often fall into the dimension trap. Then they understand that 1 cubic yard, or sorry, I should say 1 yard is actually equal to 3 foot, right? That's the linear dimension. So 1 yard is equal to 3 foot. And then sometimes they think, okay, I'm not going to fall into that trap, so I have to obviously multiply that by 3. For whatever reason, I don't understand, because they understand that we're not dealing with linear dimensions here, but we're also not dealing with square dimension with an area. We're dealing with a volume. So in reality, 1 cubic yard is actually equal to 3 foot times 3 foot times 3 foot. And so the answer is not 9 cubic foot, which is an answer I often get in the classroom. It is actually 27 foot cubed. And now you can use that 27 foot to calculate how heavy this box is, right? Because now your box is 62.4 pounds per cubic foot multiplied by 27 cubic foot per cubic yard is the way to write this. And then, of course, we have to multiply it by 3.5 because that's the multiplier of the box. And what you will find is that your box actually now has a weight of 5,900 pounds, or roughly 5,900 pounds. And that I can now continue to use to find my forces. Let's go back to our picture here, and maybe I even add this here, 5,900 pounds. And I'll say it again, this 5,900 pounds is supported by ACZ and ABZ together. So each one of them has to carry half of that, right? So I can already state that up here. I can already state that this is equal to 1/2 5,900 pounds. Now, because I have one component of the triangle given, and we already learned in so many previous classes how to convert one component into all the other components if we have the geometric arrangement given, and we definitely have the geometric arrangement given here, I can calculate all other forces. So I know again 8, 6, and 4, and I can now use that to calculate the rest. So for example, the length of the cable, right, that comes to no surprise. I can calculate the length of the cable by saying that, let's use red here, so LAB is equal to, of course, AC as well, but it's equal to 6 squared plus 4 squared plus 8 squared, and then square rooted the whole thing. So that is the square root of 98, if I'm not mistaken. So I can use that now to calculate all my components. For example, if I want to calculate the force AB, let's do that up here because it's more visual. So the force in FAB, so, or maybe I should use AC actually in this case. So let's say FAC is equal to 1/2 5,900 pounds. That is the component in this vertical force. So I'm going to divide that by 6 feet. So I divide it by 6. And now I want to find the force along this cable, which of course has a length of square root of 98. So now I multiply that by the square root of 98. And what I will find is that FAC is actually equal to 3,478. 3,478 pounds. And once again, I did that through the geometric arrangement. So I used Pythagorean in 3D up here, and then I used the components. So I used the ACZ component, divided that by its geometric description, 6, and multiplied it by the geometric description of the one that I wanted to know. So in this case, I wanted to know AC, and so it was this description right here, which was 98. All right, but what I'm interested in next is the force in this cable here, AD, and so I need to find ACX for that, right? So I need to find ACX and actually multiply that by 2 because ABX and ACX, they together pull on this cable. So let's look into that. And for example, I can calculate this one here as 1/2 5,900 divided by, and now I need to be careful again, I need to double check myself, divided by 6 multiplied by 8, because that's the direction I want to find. So multiplied by 8 divided by 6. That is the component that I need. And so now all I have to do when I want to find the answer to my AD, let me visualize that as well. So I'm going to find AD now. So this is AD, and AD is nothing else than 2 times 1/2, and I can cross that already out, 5,900 divided by 6 multiplied by 8. And if you calculate that out, you will find that we're looking at 2,213 pounds. 2,213 pounds. And that actually solves the problem, right? Because I also already know that my FAC is equal to FAB, and therefore I have proper results here. I have the result up here, and I have the result down here. And of course, in an exam, I would write that much more neatly at the bottom of the page, but I need to keep the bottom of the page to now use the equilibrium approach, the equation approach, to write these equations down so that you can actually validate your understanding of that. But this would technically be an engineering solution to the problem. We solved all the cable forces based on the fact that we have this box filled with water. Now, like I mentioned, let's complete this from an equilibrium standpoint. So if I don't know what to do on my exam, for example, the best thing to do is to blindly write out these equations. So the sum of the forces in the x direction is equal to 0, sum of the forces in the y direction is equal to 0, and the sum of the forces in the z direction is equal to 0. And of course, proper definition of the directions. And in this case, it's a little bit different than we've seen. So my y direction is actually going in this direction. My x direction is almost horizontal. And my z direction is going up. All right, now what do I have? 0 is equal to the x direction first. So plus AD, I'm going to put that at the end actually. So I'm going to start with AB, so minus ABX minus ACX and plus AD, right? Plus AD. For the y direction, I have minus ABX, sorry, ABY, plus ACY, and nothing in the AD component. But for the z direction, I have plus ABZ plus ACZ, nothing in the d direction, but I have minus 5,900 pounds, right? And again, what I now have to do to solve these equations here, notice that we have 1, 2, 3, 4, 5, 6, 7 unknowns. And obviously I cannot do that, so I have to use the geometric description to express, for example, ABX in terms of AB and ACX in terms of AC. So let's do that for one equation, and then I think we're done with this problem. So let's say that AB, of course negative, is, and be careful now, AB is this one here, which has a length of, let me get you that information on the screen. So that has a length of square root of 98. So I divide it by square root of 98, and I'm looking for the x direction, which is 8. So that means I have to multiply it by 8 and divide it by the square root of 98, right? And the same is true actually for AC. So minus AC square root of 98 multiplied by 8 plus AD. For the y direction, it would be almost the same thing, except AB divided by square root of 98. And now in the y direction, it is multiplied by 4, right? So multiplied by 4 plus AC 4 square root of 98. And last but not least, the AZ direction is also divided by 98, but multiplied by 6. And plus AC 698. All right, but we don't need to solve this now because we would just find the same answers as this. This, however, here gives you a chance to really solve these equations if you don't see the engineering or how the forces go through the system. So, and there's nothing wrong with not seeing that initially. You can definitely work your way through every problem by using this. And just to be clear here, let me add the lines through that so that I drew them too close to each other. I apologize for that. But now you have these equation sets that help you to solve this. In every case, this will always work, right? No matter what, this will always work. Whereas for the approach up here, you probably need a little bit more experience. So as a beginner, you probably use this, but try to see what I showed you here. Nevertheless, this completes our second problem of 3D particle equilibrium, and I hope that this will help you to solve your homework. I think it's ready to move on to our last problem in the set.